Our last topic is vehicle routing problems. Okay, let's start. So in many cases, we want to deliver or collect items from or to or from our customers. Okay, and we want to, of course, enhance our efficiency. So, as a very simple example, suppose you are a police officer and you want to deliver mails to 4 different addresses, okay, in today. Then, what you want to do is to try to do it as soon as possible because you have many other things to do. So, in this case, you probably construct a network, for example, like this. Okay, you have 4 different addresses and you have your own uh, post office. For each pair of 2 addresses, the shortest path can be obtained. Okay, because if you are given here and here, no matter how complicated the route is, you know what's the shortest path. No, it's just one single LP, you get it. Okay, so that's not a big deal. You can have a shortest path there, and that's make it simple. Let's just put a line there. You can have the shortest path between any pair of nodes or addresses. And then, given all these distances, you face the following routing problem. It's about to choose a route starting from the office, passing each address exactly once, and eventually returning to the office. So, for example, the route that I just depicted is here. Okay, this is a route that passed through different addresses exactly once, and then back to your original location. Alternatively, you can do another thing. Let's say something like this. Okay, then of course you also fit the objective. You also pass all the addresses. Okay, but the distance may be different. That's the difference. What you want to do is to do this in the most efficient way. So you want to find a route that can minimize the total distance or total traveling time that you need to complete the work. Okay, this is again a sequencing problem. Once you decide the orders to visit each destination, then you have that route. Okay, so in total you have this is an error, or you have 4 factorial, or that means 24 possible routes for your 4 destinations. Okay, 24 is not a very large number, but if you have 10 destinations or 20 destinations, then the total possibilities is huge. Okay, so again, this problem can or cannot be solved in polynomial time. You probably know it, you probably don't know it, but we just want to use integer programs to solve it. The problem that we just described is the famous traveling salesperson problem. Okay, it assumes that the truck has ample capacity. So that means I want to put mails into my truck, and I drive my truck to those 4 destinations and put my mails there, put their mails there. Okay. In that case, typically the truck has ample capacity, so I don't need to worry about whether the truck will be not enough to handle all those mails. But in many cases, this is not true. Like the truck towing bicycles in NTU. Okay, if you are the driver and you need to start at the car pound, pass several locations in NTU, and then return to your origin, then you know that your truck capacity would be quite likely to be not enough. Okay, because too many people are violating the parking regulation. So that means you actually may need to find multiple routes to cover all the locations. Okay, let me try to show you. For example, suppose we still have the same network here, or we still have all those distances. But one possibility is that at each location you will have demand size. Let's say something like this. This is one particular place where you may have 50 bicycles to tow, and here you have 40, and so on and so on. Suppose you only have a capacity which is let's say 10. Okay, then in each route you can handle at most 10 unit of demand. Okay, and then you need to go back to your original location to clear all those demand items, and then you go out again. So one possible way is to first go here, and then your truck is almost full, so you go back, and then you go out again, and probably like this, and then you go back. So you need 2 routes to cover all the locations. Or alternatively, you can say probably due to some special structures of your network, this is your first route, and then you go to 4 and come back directly, and then you go to 7 and come back directly. That's also possible. So when your truck is of limited capacity, this problem is of course harder, right? And the traveling salesperson problem can be said that to be a special case of vehicle routing problems. Okay, when your truck has capacities, then that's the more general vehicle routing problems. Today we will only talk about the uncapacitated traveling salesperson problem. Okay, we will show you how to use integer programming to formulate it. So how may we formulate the TSP into an integer program? Suppose we know we need to be given a directed complete network. Complete means between each pair of nodes there is an arc. Okay, so if there are n nodes, then on a directed complete network, we would have n times n minus 1 arcs. And then for each arc, we have the given arc weight, which is dij, which is non-negative. I mean here in this case, let's say it's positive. Okay, we are talking about directed network. So the distance from ij and ji may be different in general. Okay, we need to select a few arcs in the set of arcs to form a tour. In TSP, we typically call it a tour. What's a tour? That tour would pass all those cities or all those nodes and form a cycle. That's what we need. So to form a tour, we need to select n arcs, and these n arcs should form a cycle, passing all those nodes. Okay? So if you have a network, then first you are talking about directed network. So you have this direction, that direction, this direction, that direction, and so on and so on. Also, let me skip it. Your task is to select multiple arcs. Okay, for example, this one. For example, this one. And then you probably move from there to here, there to here, and then back to the origin. You're going to select exactly n arcs to form a cycle. So to define our decision variables, let's first use xij to be either 0 or 1. 1 means we want to select that arc into our tour, and 0 otherwise. If we really have it, then the objective function is very simple. We want to sum up all the distances we travel through. Okay, so that would just be to minimize the total distance we travel. That's our objective function. Then is the next question. how do we ensure that we are really creating a route? For example, should we add this constraint to require ourselves to select n arcs? Well, if you think about this problem in more details, you understand this is not enough. Let's look at this example. Suppose we are talking about list directed network, very messy, but anyway, you know, there are 4 nodes and 12 arcs. Okay, suppose arc weights are 1 for these 4 nodes and 1000 or 1 million for the other nodes. Then what you do with this constraint, will just be to select these 4 arcs. Okay? But they don't really satisfy what you need. For example, you are not passing the last city here. Okay? So obviously, only requiring to select enough number of arcs is not enough. Okay, you need to make sure that they are really creating a closed loop or creating a cycle. Let's see how to do it. Okay, so previously we failed because there is a node with no arcs adjacent to it. Okay, so let's focus on each node. For each node, now let's add the constraint here. We must select exactly 1 incoming arc. So for node K, we check all those incoming arcs. We need to select exactly 1. And also we need to select exactly 1 outgoing arc, like this. Okay? Then let's see what's going to happen. Suppose we have this very messy program. Alright, now for, let's say, a node here. I look at all those incoming arcs. This guy, and this guy. I need to select one of them. Okay, I need to select, for example, this one. And then for outgoing arcs, this one, and this one. I also need to select one of them. So let's say I select this one. Then obviously this must be satisfied for every node. So for every node, there will be an incoming arc and an outgoing arc. Then eventually every node will be on a cycle. Okay, that's just great. However, this is still not enough because we are not preventing the so-called subtours. So what's subtour? Let me illustrate this idea. One possibility that may happen in your optimal solution is that you select this arc, okay, and then this arc, and this arc, and this arc. You select 4 arcs, and if you check the condition for each node, for this one, 1 incoming, 1 outgoing, good. For this one, 1 incoming, 1 outgoing, good. These 2 are the same. So that means you are covering all the nodes with 2 cycles, with 2 subtours. Okay? But that's not what you want. You want 1 single tour to cover everyone because you want to go back to the origin. Right? So these are good and these are required, but they are not enough to eliminate subtours. We still need other constraints to prevent this to happen. Okay? Or if you are talking about a 5-node network, let me just put it as an undirected one. Your subtours may be, for example, here and here. Okay, that's also possible. So in the next video, we will tell you how to eliminate subtour. Thank you.